Welcome back to Science, to Sleep By, where we drift into the mysteries of our universe. Not to startle your mind, but to soothe it with wonder. Tonight, we venture into one of the most quietly shocking discoveries of our age. It begins with an object gliding silently through our solar system, an interstellar visitor known as 3I Atlas, and a series of amateur images that have made NASA lean in a little closer. What did those cameras capture? What secret could be hidden in a streak of light across the night sky? So, dim the lights, settle in, and let's uncover what happens when the ordinary gaze of backyard astronomers meets the guarded silence of space agencies. Because sometimes, the truth arrives uninvited. From beyond the stars, it began. As so many cosmic discoveries, with fanfare or flashing lights, but with a soft alert pinging across a quiet observatory in Hawaii. The date was April 2024, and the automated telescopes of the Asteroid Terrestrial Impact Last Alert System, known more simply as ATLAS, were sweeping the night sky, capturing thousands of images every few minutes. Their purpose, humble yet heroic, was to keep a vigilant eye out for any potential threats, asteroids that might one day draw too close to our fragile planet. But this time, the algorithm caught something different. A moving point of light, faint yet purposeful, sliding across the stars in a trajectory that didn't belong to our sun. The astronomers running the system knew instantly they had seen something unusual. This object wasn't orbiting like an ordinary asteroid. Its path wasn't bound to the familiar loops of the planets or the debris left by ancient collisions. It was coming from outside, far, far beyond. They named it 3I Atlas, the third officially recognized interstellar object ever detected entering our solar system. The 3I stands for Third Interstellar, following in the footsteps of the enigmatic one Oumuamua, discovered in 2017, and the Cometary 2I Borisov, found in 2019. Each of these visitors had carried whispers of alien worlds with them. Frozen clues to the chemistry and formation of other solar systems drifting light years away. But 3 Atlas was different, and from its very first observation, astronomers could tell that it would be a story unlike the others. What made 3I Atlas so captivating wasn't only that it came from another star, but how it moved. Its velocity was extraordinarily faster than any typical comet slingshotting through the inner solar system. Its orbit traced a hyperbolic path, meaning it would pass through our neighborhood just once before vanishing back into interstellar space, never to return. To imagine it properly, picture a stone skipping across a pond, except the pond is the solar system, and the stone has traveled for millions, maybe billions, of years through the quiet darkness between the stars. Before this single, fleeting encounter, within hours of its confirmation, observatories across the globe pointed their instruments toward the coordinates of 3I Atlas. The object was faint, nearly invisible to the naked eye, yet its presence felt monumental. Every interstellar visitor represents a physical connection between star systems, a piece of matter forged under alien suns, shaped by forces utterly unlike our own. When scientists realized this wasn't a leftover comet from the outskirts of our system, but a traveler from the deep galactic void, the data became precious. For the first time in perhaps eons, material from another world was drifting through the realm of the planets, passing near enough for us to study it, and yet, even in those early images, something didn't align neatly with expectation. Normally, interstellar objects fall into one of two broad categories: rocky like an asteroid, or icy like a comet. But 3I Atlas defied both. Its spectrum suggested a mixture of volatile ices and metallic traces, the kind of hybrid composition that didn't quite belong to any known formation model. More puzzling was its brightness. It glimmered in inconsistent bursts, at times brightening as though reflecting sunlight off flat surfaces, then dimming as if turning away. Its behavior was erratic, alive, as though the light itself was trying to speak. In the weeks that followed, observatories from Chile to Arizona captured its motion, measuring the precise angle of deflection as it curved around the sun. The numbers hinted that 3I Atlas wasn't just coasting under gravity's pull. It appeared to be accelerating slightly, ever so subtly, much like Oumuamua before it. The mystery deepened. NASA's Jet Propulsion Laboratory began tracking the object using deep space radar, though the signal was faint and intermittent. Their official statements were careful, measured, and brief. To the public, it was a rare and fascinating interstellar comet. To those studying the data, it was something far stranger. To truly understand why astronomers found this so profound, one has to imagine the scale of interstellar space. Between the nearest stars lies a gulf of trillions of miles. For a small object barely a few hundred meters wide to survive that journey intact, to resist the cosmic dust and radiation, to carry its shape and structure across such distance, implies a resilience beyond ordinary physics. If it was natural, then it was a geological marvel. If it was artificial, then it was the most profound discovery in human history. And somewhere between these two extremes lay the unknown. That's where the fascination began, not with certainty, but with curiosity. Amateur astronomers began to tune in. Small backyard observatories across the United States, in states like Arizona, Nevada, and New Mexico, captured faint streaks of light night after night, feeding their images into online repositories. They watched 3I Atlas glide past the constellations, an ember adrift on the Black Sea. They noticed its motion seemed slightly off-center, as if it rolled or pivoted with rhythm rather than randomness. Its tail, or what looked like one, appeared to break apart, not in the uniform spray of a comet, but in short, angular flares. In the US, online forums and astronomy clubs buzzed with speculation. Was it another Oumuamua? Could it be debris from a long-destroyed planet, or even an ancient probe from some civilization beyond the sun's reach? NASA stayed quiet, releasing only minimal bulletins about trajectory adjustments and visibility windows. For many, that silence became louder than any announcement. When an object from another star passes by, and the most powerful space agency in the world grows reticent, imaginations naturally ignite. The story of 3I Atlas soon became less about what it was and more about what it represented. It was a messenger, a sign that the cosmos is not static, but alive with movement and exchange. Each interstellar object that crosses our skies is a fragment of a grander cosmic circulation, pieces of other systems flung outward during planetary births and stellar deaths, drifting endlessly until gravity captures them for a brief encounter. These travelers are ancient beyond imagination, older than our planet, older than the life that now peers upward to see them. Astronomers know that our solar system, too, has cast its own emissaries into interstellar space. Fragments of asteroids, pieces of icy moons, and dust from early planetary collisions have escaped our sun's grasp and now wander other systems. 3I Atlas could be one of those same fragments, just in reverse. It might have been flung from a young star system 20 light-years away, perhaps by the gravitational slingshot of a giant planet. Over the eons, cosmic tides would have nudged it through the thin galactic disk, its surface scarred and reshaped by radiation, until fate drew it near enough for our telescopes to glimpse it. Yet, for all that science could model, some questions refused to settle. Why did its light pulse in precise intervals? Why did radar echoes suggest a more reflective geometry than expected? And why did NASA classify portions of its imaging data? The answers might be ordinary technical calibration, sensor noise, data overlap, or they might hint at something else entirely. In the gentle hush of nighttime observation, those watching 3I Atlas felt the same mix of awe and unease that always accompanies first contact, not necessarily with intelligence, but with the vastness of what we do not yet understand. The arrival of this stranger from the stars was more than a scientific event. It was an existential moment, a reminder that our solar system is not isolated, but part of a grand celestial network. Somewhere out there, other worlds spin under alien suns, and from their distant beginnings, their debris finds its way here, brushing past us like whispers in the cosmic dark. The light from 3 Atlas continued to travel across the void, faint but resolute, reflecting stories we could barely decode. Its passage a fleeting encounter in an endless galactic conversation. When 3 Atlas first entered the cosmic stage, it did so under the watchful eyes of professional astronomers and automated observatories. But it was the world of amateur skywatchers that began to reveal its most intriguing secrets. Across the United States, Europe, and parts of Asia, small backyard observatories turned their lenses toward the coordinates released by Atlas. They weren't motivated by grants or deadlines or institutional prestige. They were driven purely by wonder. To them, this wasn't just another data point. It was a visitor from another star system, a chance to capture, in their own modest telescopes, something that had journeyed across the galactic void to briefly pass near Earth. In the hills of Colorado, in the deserts of Nevada, and in the quiet suburbs of Ohio, ordinary citizens who had spent their lives looking up began to notice something strange about this new object. At first, their images matched NASA's early releases, a faint streak of light, barely distinguishable from the background stars. But as they continued to photograph 3I Atlas night after night, they began noticing subtle inconsistencies. The brightness of the object did not behave like a simple rock or comet. In some frames, it glowed intensely for fractions of a second, as though reflecting a sudden beam of sunlight off a polished surface. In others, it dimmed almost to invisibility before reappearing again in an unexpected orientation. What was odd wasn't merely the flickering, it was the rhythm. When amateur astronomers stacked hundreds of their images into time-lapse sequences, a pattern emerged. The light pulses seemed to repeat, not randomly, but periodically: faint, bright, brighter, then faint again, cycling with an almost metronomic consistency. For those accustomed to tracking asteroids and comets, this was unusual. Natural bodies tumble and rotate, but their light curves tend to fluctuate smoothly in sudden, rhythmic bursts. Something about 3I Atlas seemed to defy that expectation. One observer in Arizona, known in astronomy forums as Sky Map John, shared his composite images online. His backyard setup wasn't particularly advanced: a 12-inch telescope mounted on a tracking rig, a DSLR camera modified for long exposure, and a sky clear enough to see deep into the Milky Way. Yet his captured data showed a curious asymmetry in the reflection pattern. When compared to NASA's official light curve data, the amateur images appeared to reveal brightness variations that the professional datasets seemed to smooth over or ignore entirely. Other amateurs quickly joined in, uploading their observations, each one confirming similar flickering irregularities. Soon, the global community of skywatchers began to collaborate in ways that professional institutions often couldn't match for flexibility. Using shared cloud databases and open-source software, they pooled their images and aligned them by timestamp and coordinate. The result was a stunning, nearly continuous visual record of 3I Atlas's passage. Through collective effort, a more detailed profile began to take shape. The object wasn't behaving like a comet at all. There was no consistent tail, no steady outgassing that could explain the flicker or the slight acceleration in its trajectory. It was rotating, yes, but irregularly, almost as if under some internal guidance rather than natural spin. For NASA, such claims were speculative. For the amateurs, they were exhilarating. Many had lived through the mystery of Oumuamua years earlier and remembered how it too defied conventional classification. But this time, they felt more empowered. They had better cameras, faster computers, and more accessible data-sharing networks. The collective capacity of thousands of private telescopes now rivaled that of smaller professional observatories. In essence, the night sky had become democratized, and 3I Atlas became the first true test of this new era of distributed discovery. In France, an astrophotographer named Lucille Marquand published a paper in a peer-reviewed amateur journal summarizing her team's findings. They had noticed faint banding in their high-resolution spectral data, suggesting that the reflected light wasn't uniform across the surface of 3I Atlas. Some regions seemed to scatter light as if metallic, while others absorbed it like dark silicate rock. The spectrum hinted at the presence of alloys, materials rarely found in natural bodies of that size and composition. Her cautious conclusion was that the object's surface was heterogeneous in a manner atypical for interstellar comets. But the phrasing couldn't conceal the more tantalizing implication. Parts of 3I Atlas might not be natural at all. In the United States, astronomy podcasts began discussing the findings. The idea that regular citizens could detect anomalies missed or ignored by NASA became a cultural spark. Some speculated that NASA was withholding data for national security reasons, while others believed the agency was merely being careful, unwilling to make claims that could later be disproven. Yet, in chat groups and late-night observation sessions, the mood was different. Amateur astronomers weren't motivated by suspicion. They were motivated by curiosity. They weren't trying to expose NASA, they were trying to understand the universe. Still, questions lingered. Why did the official JPL datasets exclude certain time intervals that amateurs had clearly recorded? Why were certain NASA radar logs delayed in release? And why, in press briefings, did agency spokespeople refer to 3I Atlas in such vague terms, calling it a small interstellar body exhibiting non-gravitational motion, but providing no deeper comment on its possible cause? For some, that silence felt too careful, too curated. For others, it simply underscored how unprecedented this situation truly was. Social media magnified the intrigue. Threads filled with comparison images, speculation, and even attempts to reconstruct the object's possible three-dimensional shape. Some users produced digital models based on brightness variations, and while most were amateur approximations, a few bore uncanny resemblance to structured geometry: panels, ridges, edges. It was as if the object had facets, or perhaps symmetrical sides, faintly reflecting sunlight like a tumbling satellite. The line between science and imagination blurred, but even scientists who dismissed the wilder claims admitted that 3I Atlas behaved strangely enough to warrant the attention. What made this entire phenomenon so profound wasn't merely what was being seen, but who was seeing it. For centuries, astronomy was the domain of large institutions, national observatories, and elite scientists. But now, through inexpensive digital sensors and global connectivity, anyone with patience and passion could contribute real data to cosmic discovery. The amateurs watching 3I Atlas weren't background spectators, they were on the front line of observation. Their raw, unfiltered data offered glimpses unmediated by official channels. And when they saw something unusual, they didn't wait for permission to analyze it. They discussed, debated, and modeled it themselves. In online live streams, night after night, you could watch the glow of 3I Atlas drift slowly across the digital sky as soft piano music played and chat scrolls filled with commentary from viewers across the world. There was something poetic in it, the blending of science, art, and community. The object itself might have come from unthinkable distances, but its presence was bringing people together here on Earth. The awe was collective, the curiosity contagious. Even skeptics, while cautious, found themselves drawn into the beauty of the unknown. NASA's silence might have been procedural, a matter of incomplete data or scientific caution, but it gave the impression of a gap that the amateur community eagerly filled. They became storytellers as much as scientists, narrating the slow glide of an interstellar enigma through our solar system. Every new image, every refined dataset, added another layer to the unfolding mystery. The professionals had discovered 3I Atlas, but it was the amateurs who had really seen it in ways the institutions hadn't. Their discovery was not an accusation against NASA, but a revelation about human nature. Curiosity is universal. Whether through a billion-dollar space telescope or a homemade mount in a suburban backyard, that same desire to look up and understand the universe persists. The sky belongs to everyone, and sometimes, it takes many eyes, professional and amateur alike, to notice when something in it doesn't quite fit the pattern we expect. As the days passed, 3I Atlas continued on its lonely trajectory, fading slowly into the darkness from which it came. But the images remained, stored in thousands of computers and cloud drives, pixelated fragments of a mystery that refused to be contained by official channels. Somewhere in those streaks of light lay hints of shape, symmetry, and purpose, clues that maybe, just maybe, the amateurs had caught a glimpse of something extraordinary, something that would make even NASA pause before deciding what to say next. When the story of 3I Atlas began circulating through the astronomy community, the excitement was immediate and widespread. For NASA, however, excitement was never the first reaction. It was calculation, precision, a methodical silence. Within days of the object's discovery by the Atlas telescope in Hawaii, data streams were flowing into NASA's Jet Propulsion Laboratory in Pasadena, California. The agency's automated systems confirmed the same conclusion as the amateurs already celebrating online. 3. Atlas was not gravitationally bound to our sun. It was interstellar. But what came next would unfold behind closed doors, in quiet conference rooms, through private communications between NASA's researchers and affiliated observatories. There was no public statement at first, only data numbers tucked into databases and observation logs that few outside the agency would ever see. At JPL, mission scientists began modeling the object's orbit. Their simulations showed a trajectory that didn't quite align with the initial Atlas readings. Something in its motion hinted at small, irregular accelerations, subtle enough to be overlooked in early analysis, but persistent across multiple datasets. These minute deviations reminded several researchers of Oumuamua's puzzling course shift in 2017, which had sparked heated debates about whether natural forces alone could account for its behavior. No one wanted to repeat that controversy. This time, NASA decided to proceed with extreme caution. Behind the scenes, telescopes around the world were tasked to monitor the object under NASA's coordination. The Pan-STARRS Observatory in Hawaii, the Canada-France-Hawaii Telescope, and radar facilities operated under NASA's Near-Earth Object Program. The object's surface appeared to reflect sunlight unusually efficiently, as though composed of material more reflective than typical comet dust or rock. The signal-to-noise ratio in the radar data fluctuated unpredictably, suggesting that the object's orientation might be changing in complex ways. For most objects, this would have been enough to trigger an early press release. But NASA waited. The first official notice came 2 weeks later, a short, clinical update released through the Minor Planet Center. It confirmed the hyperbolic orbit, acknowledged the interstellar origin, and provided updated trajectory data. But there was no discussion of composition, reflectivity, or non-gravitational acceleration. In fact, certain parameters that amateur astronomers expected to see, albedo values, rotation period estimates, and light curve details, were missing altogether. When researchers outside NASA requested access to raw data for independent analysis, they were informed that the information was being reviewed for instrument calibration verification. To the public, this might have seemed routine, but within the scientific community, such prolonged withholding of fundamental observation data raised eyebrows. Across social media, speculation began to ripple. Amateur astronomers compared NASA's brief updates to their own growing catalog of images and time-lapse observations. They noticed discrepancies, brightness variations, and reflection patterns that NASA's data summaries did not acknowledge. Some began to wonder whether the agency had detected something in 3I Atlas that required more careful handling. Others thought it was simply scientific prudence, an attempt to avoid another public relations storm like the one surrounding Oumuamua. But in forums, podcasts, and late-night discussions, the term NASA's secret began to circulate. Inside NASA, the atmosphere was far from conspiratorial. It was cautious, analytical, and at times, divided. Some researchers believed that the object's odd behavior could be explained by uneven outgassing jets of sublimating material pushing it slightly off course, similar to a comet venting gas as it warmed near the sun. Others weren't so sure. The observed light curve was irregular in ways that standard comet models couldn't fully account for. The changes in brightness were too abrupt, and the lack of detectable gaseous emissions complicated the explanation. If it wasn't outgassing, what else could be causing the acceleration? At the same time, certain classified sensors not officially associated with NASA government-owned orbital telescopes that monitor near-Earth space had also detected 3I Atlas. These instruments captured infrared signatures that reportedly differed from standard asteroid thermal emissions. Whether those readings reached NASA directly or through interagency communication remains unknown, but soon after, NASA's data handling protocols around 3I Atlas changed. Requests for additional observations from non-affiliated observatories began to be filtered, and some communication threads between NASA scientists and the broader community grew abruptly quiet. The artificial hypothesis had haunted NASA once before, when Oumuamua displayed unexplained acceleration. A few researchers, most notably Harvard's Avi Loeb, dared to propose that it might have been a piece of alien technology, a solar sail, a probe, or a fragment of something engineered. The scientific establishment reacted with discomfort, if not outright resistance. That debate left a scar on institutional credibility. With 3I Atlas showing similar, but not identical peculiarities, NASA's administrators were determined not to let the conversation spiral into sensationalism again. Yet this determination to remain conservative produced its own consequence: silence. And in silence, speculation thrives. While NASA's official communications froze, its data pipelines did not. Within the organization, scientists quietly analyzed spectral returns, radar echoes, and trajectory shifts. Some found minor inconsistencies that could not be reconciled with purely natural models. A few internal memos circulated among teams noting that the object's surface albedo was unusually high for a body exposed to interstellar radiation for millions of years. Such exposure tends to darken and redden cosmic material, but 3I Atlas reflected light more like a young, freshly exposed surface, or perhaps a surface coated in something smooth and resilient. This detail was left out of the public summaries. Another point of intrigue came from the object's tumbling pattern. Normally, when objects rotate, their light curves produce predictable sinusoidal patterns as they expose different faces to the sun. But 3I Atlas's brightness variation was asymmetrical, suggesting a more complex geometry, possibly elongated, possibly flat. The more researchers tried to model it, the less natural it seemed. Yet NASA chose to emphasize the need for further observation, avoiding any language that could invite the wrong interpretation. For the amateur community, the quietness was deafening. People who had spent their nights photographing the same object that NASA was studying began to feel a curious dissonance between what they saw and what they were told. In discussion boards, some began to wonder if perhaps the object had displayed behavior's small course corrections, flickers of light indicative of some active mechanism. NASA, of course, never acknowledged such possibilities publicly, but it didn't have to. The lack of answers became its own form of confirmation for those inclined to believe something was being hidden. Still, there were practical reasons for the secrecy. NASA, bound by interagency agreements and international observation protocols, cannot always release raw data immediately. Radar tracking from military-linked facilities, for example, often includes classified coordinates. Moreover, the early phase of analysis demands careful calibration to rule out false positives. In a sense, NASA's restraint was scientific caution masquerading as mystery. Yet, as days turned to weeks, the world watching 3I Atlas saw the agency's silence as something more deliberate, a quiet observation of something extraordinary. Within NASA's own halls, conversations grew more philosophical. Scientists who had dedicated their careers to understanding natural celestial mechanics found themselves revisiting questions they thought they'd never ask. Could the universe, vast and ancient, truly be silent except for us? Could interstellar objects like 3I Atlas be fragments of something intentional, evidence not of visitors, but of messengers lost to time? These were not ideas that made it into official briefings. They were musings shared over late coffee, under the hum of laboratory lights, as researchers stared at anomalous light curve graphs glowing softly on their screens. Meanwhile, journalists began probing. Requests for comment went unanswered or were met with familiar phrases. Data under review. Further confirmation required. No official statement at this time. The object's story slipped between the cracks of public attention, overshadowed by more terrestrial headlines. But among those who continued to watch, NASA's restraint only deepened the fascination. The notion that a government agency one founded to explore space openly, and for all humanity, might be sitting on something extraordinary carried an undeniable allure. Yet, to those inside the process, The truth was quieter, subtler, more human. Scientists weren't hiding evidence of alien artifacts. They were confronting uncertainty, and uncertainty that challenged the very limits of their models and their understanding. What they feared wasn't exposure, but error. The wrong announcement, the wrong interpretation, could mislead the world and damage decades of trust in scientific rigor. So NASA chose the path of silence, knowing that in the space between words, the public would fill the void with wonder, doubt, and imagination. S3I Atlas moved farther from the sun, fading into the black expanse from which it came. NASA's official updates dwindled to almost nothing. The world moved on, but within those who studied it, professionals and amateurs alike, remained a sense that something in that faint object had stirred deeper questions. Questions too delicate to answer aloud. It was as if NASA's silence itself had become part of the mystery, a whisper echoing between stars and scientists, between what is known and what remains unsaid. As 3I Atlas drifted deeper into the solar system, crossing invisible boundaries of planetary orbits and gliding through the light of our sun, the telescopic gaze of both professionals and amateurs grew sharper. By late May 2024, composite images began circulating online that hinted at something entirely unexpected. Within the faint streaks of the object's motion, buried in layers of pixel noise and background starlight, there appeared to be structure. Not the rough, irregular contours of an asteroid or the fuzzy halo of a comet, but something else. The first person to notice it was an Italian astrophotographer named Renzo Salvi, who, while stacking hundreds of long exposure frames, saw what looked like alternating light and dark bands repeating across the object's shape. He thought it was a data artifact, a product of digital interference or atmospheric turbulence. Yet, when he cross-referenced his images with data uploaded by observers in Japan and Chile, he found the same faint pattern. At first, the scientific community dismissed these findings as coincidence. Interference patterns, after all, are common in amateur astrophotography. But as more observers replicated the results under different atmospheric conditions, the conversation began to shift. The bands were real, or at least, they were consistently appearing across unrelated observations. Some described them as reflective ridges, others as panels. Whatever they were, they hinted at an unexpected regularity, geometry in a place where nature prefers chaos. NASA's official images, released selectively through their data portal, showed none of these patterns. The object appeared as a bright dot, elongated slightly by motion blur. But amateur astronomers with powerful tracking mounts and sensitive CCD sensors managed to freeze the object's motion more precisely, capturing brief exposures during its slow rotation. These images revealed flashes of light that did not correspond to random tumbling. Instead, they suggested that 3I Atlas was reflecting sunlight from specific, planar surfaces, flashes that occurred in timed intervals, as though multiple flat faces were catching and redirecting light during rotation. For scientists accustomed to studying natural celestial bodies, this presented a problem. No known process could create an interstellar object with such symmetry. Rocks and comets form through collisions, gravitational compression, and chemical bonding, all of which produce irregular shapes. Even large asteroids in our own system like Vesta or Eros bear the marks of random impacts, their surfaces uneven and jagged. But the early images of 3I Atlas hinted at something smoother, as if its edges had been defined by intention rather than accident. Researchers at independent observatories attempted to model the light curves mathematically, using variations in brightness to infer shape and rotation. The resulting models were baffling. In some simulations, the data fit an elongated, cigar-like body similar to Oumuamua. In others, a thin, disc-shaped structure best matched the observed reflection patterns. A few models even suggested a complex geometry, multi-angled planes or facets that seemed far too organized for a natural fragment. What made these models truly perplexing was their consistency. Across observations from different hemispheres, it was as though the object was rotating in a deliberate rhythm, exposing reflective surfaces at intervals that repeated predictably. At NASA's Jet Propulsion Laboratory, Data analysts compared their own high-resolution infrared readings with the public light curves. Privately, some researchers began to admit that the reflection behavior didn't make sense for a natural object. The surface seemed to exhibit variable reflectivity, possibly due to differing material composition across its structure. Parts of it reflected heat poorly, while others did so with extreme efficiency, suggesting alternating materials, perhaps metallic regions interspersed with something darker and absorbent. Such alternating reflectivity is rare in naturally occurring bodies, but characteristic of engineered surfaces. Meanwhile, the amateur community was conducting its own form of peer review. They collaborated across time zones, comparing results and running experiments to rule out optical artifacts. In Texas, an engineer named Caroline Dawson, who operated a remote telescope array, applied deconvolution algorithms to the raw data. When she presented her processed images on an online astronomy forum, the results caused a quiet uproar. Her composite appeared to show linear boundaries edges that formed an angular silhouette inconsistent with any known comet or asteroid. The object's brightness peaked sharply at intervals that matched the rotation of what she described as structured symmetry. Astrophysicists cautioned against premature conclusions. Human perception, they explained, often interprets patterns in randomness, a phenomenon known as pareidolia. But even skeptics had difficulty explaining the uniformity of the reflections. The object's periodic glints were not random. They occurred at precise intervals, measurable to fractions of a second, and their intensity followed a mathematical regularity. The intervals suggested that 3I Atlas might be rotating once every 10.4 hours, completing a full revolution while producing distinct reflection peaks 4 times per cycle. If those peaks corresponded to flat surfaces, then the object had at least 4 major reflective planes. As word of these findings spread, NASA quietly adjusted its observation priorities. The Goldstone Solar System radar in California conducted several attempts to image the object directly, though the signal return was weak due to its distance and speed. The radar data hinted at a shape that was more extended than spherical, possibly with sharp variations in surface contour. In internal memos later leaked to scientific bloggers, one line stood out: 3I Atlas displays reflection anomalies inconsistent with expected scattering behavior for a natural interstellar body. It was a technical sentence, cautious and hedged with uncertainty, but its implication was enormous for those following the story from the outside. NASA's silence only amplified the intrigue. When an object from another star exhibits geometric reflection and the world's leading space agency avoids direct commentary, imagination naturally fills the gaps. Some theorize that 3I Atlas was a fragment of alien technology, perhaps a derelict probe, its structure fractured but partially intact. Others proposed a more modest hypothesis, that it was debris from a long-dead exoplanet civilization, or even a relic of interstellar industry drifting endlessly through space. A few skeptics argued it could be a sliver of planetary crust stripped by a supernova's shockwave, its reflective pattern the result of crystalline layering. Whatever the explanation, the shape defied the easy categories of comet and asteroid alike. Amateurs continued their vigil. Each clear night, their telescopes captured the faint glow, their software tracking the object's movement across constellations. In the quiet of those hours, as Earth rotated beneath them, they documented something unthinkable, a possible glimpse of constructed order emerging from the chaos of the cosmos. Their excitement was tempered by disbelief. After all, extraordinary claims demand extraordinary evidence. Yet, the data persisted, stubborn and silent. The shape of 3I Atlas refused to conform to expectation. NASA's internal discussions reportedly grew more complex as new data arrived. Some scientists argued that the object might be coated in volatile material that sublimated unevenly, producing temporary reflective planes as ice vaporized and refroze. Others suspected that micrometeor impacts had chipped away portions of its surface, exposing highly reflective crystalline regions. But neither hypothesis fully explained the precision of the reflections. The geometry seemed too consistent, the intervals too precise. Meanwhile, a growing number of astronomers outside the agency urged NASA to release its full data set for independent verification. Public pressure increased when certain files on NASA's data server were temporarily redacted without explanation. The timing coincided with the discovery of the structured reflections, prompting theories that NASA had discovered something too significant to release unfiltered. For the agency, such accusations were nothing new. Secrecy, after all, often follows complexity. But in this case, the silence resonated differently. It felt purposeful. By June, several high-powered observatories attempted to capture additional imagery before 3I Atlas drifted beyond reach. The European Southern Observatory managed to obtain faint spectroscopic data that revealed unexpected absorption lines. Some researchers believe these lines indicated traces of nickel or chromium metals, not uncommon in asteroids, but rare in the specific ratios detected. If accurate, it would suggest that 3I Atlas's composition was partly metallic alloy, not the random mix of silicates and ices expected from a natural body. In the United States, the story began reaching mainstream media, though most outlets treated it cautiously, emphasizing the speculative nature of the findings. Still, headlines carried an unmistakable sense of awe. Interstellar visitor exhibits unusual geometry. Scientists puzzled by possible structured shape. NASA declines to comment on 3I Atlas anomalies. Each article added momentum to a growing global curiosity. For many, this was the first time the public had collectively imagined the possibility that something designed, something made, might have entered our solar system. For the scientific community, the implications were staggering. If the geometric reflections were real, they would challenge the boundaries of planetary science and astrophysics alike. Could a natural process somewhere in the galaxy produce objects with structured symmetry? Could interstellar collisions or pressure differentials somehow sculpt matter into organized planes? Or was this the first evidence of interstellar engineering, ancient and drifting, passing silently through our neighborhood like a relic from a civilization that had mastered travel between the stars? The longer scientists looked, the fewer answers they found. The data refused to yield a simple explanation. Each observation seemed to deepen the enigma, every hypothesis breaking apart against new evidence. The shape of 3I Atlas was more than a physical form, it was a question carved into light and distance, hovering between science and the unknown, daring humanity to decide what it was seeing. In the weeks following the growing fascination with 3I Atlas's geometry, a strange and unsettling development began to unfold quietly across online scientific communities. Amateur astronomers who had been freely sharing their tracking data and raw image files began to report something unusual. Links were disappearing, file repositories were being taken offline, and in some cases, uploaded datasets were being removed from public astronomy databases. What had started as a grassroots collaboration, a global exchange of open-source data about an interstellar object, was suddenly fragmenting under the weight of silence. No one knew exactly who or what was responsible, but the timing was impossible to ignore. It began right after NASA's radar analysis memo leaked, the one hinting that 3I Atlas displayed reflection anomalies inconsistent with expected scattering behavior. At first, it seemed like a technical issue. Amateur astronomers assumed it was server overload from the flood of attention. Forums discussing the object had surged in traffic. Reddit threads, YouTube channels, and online observatories were hosting live feeds and detailed breakdowns of each new data point. But then, quietly, links to high-resolution image sets vanished, not only from small private servers, but even from the NASA-affiliated Minor Planet Center, which had been publishing observational updates. The official explanation was routine database maintenance. Yet, when access returned days later, some of the archived data was missing. Observation records from key dates in late May and early June had been redacted or replaced with placeholders marked "Data Recalibration Pending." This was the spark that ignited a storm of speculation on astronomy forums and digital citizen science communities. Users began comparing cached versions of the missing files. Some had backups, downloaded copies of images and brightness profiles that appeared to differ from what was later re-uploaded. The discrepancies were subtle but measurable. In the newer files, certain peaks in brightness had been smoothed out, as though the reflective intervals previously observed had been statistically normalized. The result was an object that looked less geometric, more random. To the naked eye, the difference was small, but to the researchers who had been studying those very reflections, it was as if someone had erased part of the story written in the light. Among the first to notice was a postgraduate researcher named Alex Rivera from Arizona State University. Rivera had been tracking 3I Atlas since its initial discovery, analyzing photometric variations in the light curve. When he cross-referenced NASA's reposted data with the earlier open-source versions, he found several discrepancies. In one case, an entire segment of readings spanning roughly 6 hours of continuous observation had been removed. When Rivera inquired through official channels, the response he received was curt: "Data under verification." The message contained no timeline for republication. Around the same time, several amateur astronomers reported receiving polite but firm requests from moderators on NASA's citizen science platforms to refrain from speculative analysis until peer-reviewed results were available. For some, the message carried an unspoken warning: stop connecting the dots. The forums where the geometric reflections had first been discussed began locking threads, citing content moderation policies. The public discourse surrounding 3I Atlas was being gently but firmly pushed back into silence. Meanwhile, NASA's own updates became noticeably less detailed. The agency shifted from releasing raw observational data to short, standardized summaries, trajectory updates, orbital parameters, and general brightness statistics. No mention of reflective anomalies. No mention of surface geometry. When reporters pressed for clarification during a live-streamed Q&A, the spokesperson repeated that no definitive evidence supports the presence of artificial features, but the phrasing struck many as evasive. It neither denied nor confirmed the anomalies, only deferred them. Behind the scenes, independent researchers continued to piece together fragments of missing data. Some uploaded their saved copies to encrypted drives, others archived everything offline. It became a digital cat-and-mouse game between those determined to preserve transparency and the invisible mechanisms of institutional control. On social media, hashtags like #3iAtlas.agate and #WhereIsTheData began trending within astronomy circles. For the first time in years, the amateur scientific community, normally cooperative and apolitical, was openly questioning NASA's handling of information. The tension grew sharper when a set of private emails surfaced on a public astronomy Discord server. The emails, allegedly exchanged between researchers at a NASA-affiliated observatory, discussed anomalous albedo corrections applied to recent 3I Atlas datasets. Albedo, the measure of reflectivity, was precisely what amateur astronomers had been studying. The leaked correspondence mentioned recalibrations designed to filter out transient spikes inconsistent with known physical scattering models. In other words, someone had manually adjusted the data to remove irregularities that happened to be the very signatures pointing to geometric reflections. The implications were staggering. If authentic, these edits suggested that NASA, or at least some of its contracted analysts, were deliberately smoothing out the anomalies before releasing public data. Officially, the justification might have been methodological consistency, but to outside observers, it looked like selective omission. The public was not being shown the full picture. As the controversy spread, NASA released a brief statement emphasizing that all data revisions were conducted in accordance with standard photometric calibration procedures. They reassured the community that no scientific information had been withheld. But for many, the damage was already done. The disappearance and alteration of public data, combined with the agency's reserve tone, had eroded trust. To the scientific mind, uncertainty is acceptable but censorship is not. Amid this tension, another odd event occurred. Several high-profile astronomy YouTube channels which had uploaded detailed breakdowns of the geometric reflection patterns, reported that their videos had been flagged for misinformation. In some cases, the videos were temporarily removed, only to reappear later with reduced visibility in search results. The creators were bewildered. Their content was based entirely on publicly available data and standard analytical methods. Yet, they were being penalized under policies typically reserved for conspiracy theories. The message was clear. The conversation was being managed. It wasn't just digital data that vanished. A few amateur observatories in South America reported that they had been contacted by local scientific liaisons affiliated with international research networks, requesting access to their raw observation logs for verification. After submission, some never received their files back. These were not government facilities, but private institutions, small observatories run by passionate volunteers. To them, it felt invasive, as if their data had suddenly become part of something larger, something controlled. By mid-July, the story had split into two parallel realities. In one, NASA continued its calm, official narrative, an interstellar object, fascinating but natural, now exiting the solar system. In the other, an expanding network of independent researchers was tracing a trail of missing data and digital erasure. Between these two realities lay the public, uncertain whom to believe. Scientists sympathetic to NASA argued that the missing files were simply artifacts of complex data management. The agency handles thousands of observations daily, and occasional archival issues are common. But others countered that the pattern was too specific, too selective. The files missing or altered were precisely those documenting the most anomalous findings. AS3I Atlas faded from visibility. The urgency to preserve its digital fingerprint intensified. Amateur astronomers across continents began compiling what they called the Atlas Archive, a decentralized, open-access repository containing every known observation, timestamp, and spectral analysis of the object, including the versions removed or altered from official sources. They believed that if the truth about 3I Atlas were ever to be known, it would survive through this archive, independent of institutional oversight. Meanwhile, whispers of an internal NASA directive began circulating online. A document titled OPSEC Protocol 2I3I Observations was rumored to restrict communication regarding unverified non-natural surface characteristics, though its authenticity was never confirmed. The document's existence became legend. Within astronomy communities, a symbol of the tension between open inquiry and bureaucratic control. For ordinary Americans following the story through podcasts and late-night talk shows, the narrative took on a distinctly cinematic quality. The idea that NASA might be concealing information about an interstellar object ignited the public imagination. Talk radio hosts debated whether 3I Atlas represented alien technology or an unacknowledged classified satellite. Conspiracy theorists latched onto the phrase, data that disappeared, weaving elaborate tales of hidden agendas. Scientists cringed at the sensationalism, but privately shared the unease. In universities, professors began using the controversy as a teaching moment, an example of how science, secrecy, and public perception can collide. They reminded students that the line between caution and concealment can blur easily when the unknown challenges established frameworks. They also noted that the situation revealed an important truth. In the digital age, information suppression is nearly impossible to complete. Every byte leaves a trace, every deleted file a shadow. And so, while NASA's official record of 3I Atlas grew cleaner and simpler with each update, the shadow archive continued to grow in the background. On hidden servers and encrypted drives, amateur scientists kept their raw images safe, along with their hope that one day, the world might see the unfiltered truth. Whether the missing data had been erased for reasons of accuracy, caution, or something far less innocent, no one could say for certain. All that remained was the lingering sense that somewhere between the stars and our screens, something extraordinary had been found and quietly hidden from view. As the controversy surrounding 3I Atlas's missing data deepened, A new layer of mystery emerged, one that did not rely on light, reflection, or imagery at all. It began with radio signals. Not transmissions in the sense of deliberate communication, but faint, almost imperceptible fluctuations buried deep in the electromagnetic background that astronomers constantly monitor. Radio telescopes around the world continuously scan the sky for natural emissions, bursts from pulsars, static from quasars, whispers from cosmic microwave background radiation. But in mid-June, several amateur and professional observatories reported detecting something subtle, yet distinctly unusual, coinciding with the exact trajectory of 3I Atlas. The anomaly wasn't loud or structured like a broadcast. It was a faint, rhythmic modulation in the noise, a signature that seemed to rise and fall in lockstep with the object's passage through space. At first, this was dismissed as coincidence. Space is filled with noise, and most signals detected by Earth's radio telescopes are either cosmic or terrestrial interference. However, the same modulation began to appear independently in data gathered from 3 observatories located thousands of miles apart: the Allen Telescope Array in California, the Parkes Observatory in Australia, and the Sardinia Radio Telescope in Italy. When the raw data from these observatories were cross-referenced, the modulation frequency aligned almost perfectly, with an interval repeating every 10.4 hours the same rotation period inferred from the object's reflective light patterns. That single coincidence was enough to send ripples through the scientific community. A rotating interstellar object producing synchronized radio fluctuations suggested one of two possibilities. Either 3I Atlas possessed unique electromagnetic properties that interacted with the solar wind in ways never before observed, or it was emitting the fluctuations intentionally, or at least through an engineered process. The distinction between natural and artificial was blurred, but the synchronization was undeniable. NASA did not immediately comment on the reports. Officially, their Deep Space Network, which tracks spacecraft across the solar system, had not detected any anomalous transmissions. But that statement was carefully phrased. The DSN primarily listens for strong, coherent signals from known transmitters, space probes, satellites, and planetary radars. The fluctuations attributed to 3I Atlas were neither strong nor coherent. They were faint pulses buried within cosmic noise, measurable only after extensive filtering and amplification. Amateur radio astronomers described them as breathing, static, gentle waves rising and falling like a cosmic heartbeat. The first serious investigation into these frequencies came not from NASA, but from SETI researchers. The search for extraterrestrial intelligence had been dormant in the mainstream conversation for years, its work often overshadowed by more conventional astrophysics. Yet the alignment of rotation and radio modulation reignited interest. The SETI Institute ran targeted scans of 3I Atlas using their facilities in California and New Mexico, looking for structured patterns within the noise. Early analyses revealed no digital encoding or narrowband transmission typical of artificial signals. But one researcher, Dr. Eleanor Brooks, noted an odd phase coherence, a consistent timing pattern between signal peaks that suggested a stable source rather than random fluctuation. Dr. Brooks described it in an interview as a whisper to organize to ignore. Her team's findings were submitted for peer review, but were never formally published. According to sources familiar with the matter, NASA requested additional verification before any public release, citing the risk of misinterpretation. Weeks later, SETI quietly updated their public logs, removing 3I Atlas from the list of active observational targets, stating that no further anomalies were detected. For independent researchers, however, that was not the end. Using publicly available radio telescope networks like the European Radio Astronomy Club (ERAC) and citizen science initiatives such as SkyPipe, hobbyists began recording their own frequency sweeps. They noticed that the faint modulation signature persisted even after NASA's withdrawal, though it was weakening as the object moved farther from Earth. These enthusiasts meticulously logged their data, overlaying it with the predicted rotational and orbital models of 3I Atlas. The correlation remained uncanny. every 10.4 hours. The faint pulse repeated. As the community dug deeper, new theories began to emerge. Some speculated that the modulation could be a byproduct of magnetic induction, a natural phenomenon that occurs when metallic objects rotate through variable magnetic fields. If 3I Atlas contained metallic alloys, as spectral hints suggested, it could theoretically generate weak electromagnetic emissions as it spun through the charged plasma of the solar wind. This was a plausible explanation, though it required a level of metallic purity rarely found in naturally occurring interstellar objects. Others argued that if the structure truly had geometric planes or facets, those could act like antennas, resonating at specific frequencies as they interacted with solar radiation. Yet, a smaller but vocal contingent proposed something more radical. They suggested that 3I Atlas might not simply be reflecting sunlight, but also responding to it, absorbing and radiating energy in a controlled way. This would imply some degree of technological sophistication, perhaps an ancient relic harnessing solar energy for propulsion, communication, or self-regulation. The idea bordered on science fiction, but so had much of modern astronomy before evidence turned imagination into reality. Within the walls of NASA's Jet Propulsion Laboratory, discussions grew more intense. Internal emails, later leaked to journalists, revealed that radio teams had indeed detected weak, structured periodic noise consistent with the public observations. One analyst described it as quasi-coherent modulation exhibiting phase stability across 48-hour intervals. In simpler terms, the signal remained steady, predictable, and synchronized with the object's rotation. What troubled researchers most was its persistence. Natural emissions, such as those from comets or charged dust, fluctuate chaotically. 3I Atlas's signal did not. Despite this, NASA's public stance remained firm. There was no evidence of artificiality. When pressed by reporters, they emphasized that interstellar objects are poorly understood and may display unfamiliar physical interactions. It was a cautious statement, scientifically accurate, yet intentionally vague. Behind closed doors, several senior scientists advocated for continued observation using the Deep Space Network's 70-meter antenna in Madrid. However, those requests were reportedly deprioritized, as the object's trajectory placed it at an increasingly awkward angle relative to Earth's position, requiring excessive resource allocation. In bureaucratic terms, 3I Atlas was slipping beyond official interest. As we bring this exploration to a close, we return to the simple yet profound truth that began this entire journey. Curiosity is humanity's oldest language. The mystery of 3I Atlas, whether a natural wanderer or a messenger from beyond, reminds us that discovery doesn't always arrive in grand gestures or dramatic revelations. Sometimes, it arrives quietly through the lens of an amateur telescope, in the hum of leaked data, or within the restless questions that refuse to fade from our collective mind. For the scientists, it was a test of integrity, how to balance the pursuit of truth with the caution demanded by uncertainty. For the public, it was a moment of awakening, a reminder that the universe still holds wonders that can humble in the most advanced technology. For dreamers and skeptics alike, it was proof that mystery still lives among the stars, waiting for the human gaze to meet it halfway. In a world often fractured by disbelief and distraction, the story of 3I Atlas united people across borders and disciplines under one shared question: what if we are not alone? And even if the object was simply a relic of cosmic chance, its presence still achieved something extraordinary. It rekindled wonder. It reignited the dialogue between science and imagination, between evidence and belief, between the known and the possible. Perhaps NASA's greatest secret was never about hiding the truth, but about reminding us that truth itself is a journey, not a destination. Every mystery we encounter in the night sky challenges us to look beyond the surface, to ask better questions, and to stay open to possibilities that transcend the limits of our current understanding. So tonight, as you drift toward sleep, imagine the vastness of that interstellar traveler, still moving silently through the darkness, an ember of the unknown gliding between worlds. Let its story remind you that the universe is not finished speaking. The next signal, the next spark, the next visitor could already be on its way. And when it arrives, may we once again meet it, not with fear or secrecy, but with the boundless curiosity that defines what it truly means to be human.